Welcome everyone to our second lecture of the day, and it's a pleasure to have Jinho Baik coming to us from Michigan or wherever in the world you want it to be, I suppose. You know, the rules of the game are the same as it's been. If you haven't been on, just unmute yourself if you want to talk, and if you want to ask a question. Otherwise, keep yourself mute. And if you have a question that is not as pressing or you think other people might be able to address, just click on the chat and make sure to chat everyone. If you just chat Jinho, he might not see the chat until the end of the talk. Okay, so I sent in the chat, I think I shared, and maybe I'll share this once more. I don't know if people who came later got it, but these are Jinho's slides. You're welcome to follow along that way as well. Okay, so Jinho will speak to us about relaxation time limit of periodic TASEP. So take it away, Jinho.
Okay, all right. So first, I'd like to thank the organizers, Ivan and Alexei, for inviting me here. And thanks for everyone. And I hope that everyone is having a good time. Not so bad in this situation now. Yes, I'm going to talk about periodic TASEP. Let's see. Yeah, right. So this is joint work with several people. So first, it's with Zipeng Liu, and Zipeng and I wrote a few papers on this subject, and we'll talk just briefly mention some of them. And then the most of the talk will be about this paper 3, which is joint work in preparation with Guillaume Silva and Zipeng Liu. It should be coming out in maybe a few days, I hope. And then at the very end, I'll probably mention maybe in one slide that there's another one in preparation with Andrei Prokhorov and Guillaume Silva. Okay, so let's see, next page here. Right, so this is a TASEP on a periodic domain, or equivalent TASEP on a ring. So imagine that there is a ring. That means that discrete nodes that is looped around, and suppose there are L such points, and some parts are occupied by particles, and they follow the usual TASEP rules. So they jump, in this case, counterclockwise. And then you can see that after a while, the particle jump around and then catch its own tail of the group, and then it starts to interacting with that portion. Right, so equivalent, you can think it as a spatially periodic TASEP. So this picture here, that the period is L, and if one particle moves, then all the other particles in the same location, the different period will move exactly at the same time. Okay. Right. So, so what is the interesting limit that one can think about? So there are two possible cases. The one is that the when time is not too large compared to the period. If period is really long, then you are not going to see the periodicity or the ring size effect at all. So then the problem should be same as infinite line case. On the other hand, when L is much smaller than t time, say L is fixed and time goes to infinity, then it is essentially a finite domain problem. So eventually, after a long time, it will reach an equilibrium. So the dynamics is not from KPG dynamics, but rather equilibrium dynamics. So it will be very different. So there should be a transition between these two situations. And one can imagine when that happens. So in the KPG scaling, when the two particles at the distance of order t to the 2/3 after time t, that's a spatial correlation in the KPG scale. So after time t, particles at the distance of order t to the 2/3 are critically correlated. So it's less than then they are strongly correlated. If they are further than that, then they are not correlated. So the t to the 2/3 is a scale that they are critically correlated. If we are in the situation that this t to the 2/3 is same order as the ring size L, that would mean that all particles in the system are critically correlated. So that's an interesting limit. And in that case, then that's the case that we are going to be considering. Right? So the plan of this talk is the following. So first, we'll discuss the relaxation time limit, which is the time and period both tends to infinity in the critical way such that time is proportional to of the same order as L to the 3/2. Okay. And then my goal is here is not to describe the proofs of that statement or anything like that, but rather I want to just make a comparison of the final formula with the infinite line situation. So I'll focus on the one-point distribution most of the times, especially with the step initial condition. And then I'm looking at the limiting formula of that. And then compare the formula with the trace rhythm distribution, which comes from the infinite line KPG fixed point. Okay, so I'm going to address the similarities and differences of the one-point distribution in the periodic case, in the relaxation time limit, and also the FGUE. And then I'll discuss some of the properties of the periodic case, small time limit, large time limit, and right tail. And then maybe later, like 15 minutes of the talk, I'll focus on the integrable differential equation structures that comes from both periodic and infinite line case. All right, so I said I'm going to focus on the periodic TASEP with the step initial condition. So step initial condition here is that there are a bunch of particles and a bunch of holes in the one period. It's in the picture. So the density profile look at time 0 looks like the first picture here. Right, so it's 0 and 1 and 0 and 1, the pattern happens. And the next two pictures are the sort of the average density profile as time increases. And then the bottom pictures are the corresponding pictures for the height function. So this is not the simulations, but it's rather the average height functions as at various time points. And then you can imagine, you can see that this wedge part here, you can imagine if this period is really long, then those effects will not appear. But there are these two locations when you can see shocks forming. And those are natural because unlike the infinite TASEP with step initial condition, which does not have any shocks, with the periodic case, the location like this is exactly the place that you cannot have shocks. Okay, that's a small difference. Okay, that will come up as the point later. All right. Okay, so here's a result about the one-point distribution, the limit theorem. So we consider the periodic TASEP with the period L, and then particle density rho. So there are n rho times L number of particles per period. And let's denote H of PT with the height function at the location P at time T. Right? And then we assume the initially this follows from the step initial condition. And then we scale the time and location height as the usual scaling. So the time is, well, usual scaling, but then they will be proportional. They will be depending on the period because we want to make a period L to infinity. So time, so the before scaling, we have T and P and X. Those are the time and location and height variables. The scaled time and location height variables are denoted by tau and gamma and little x. And they are multiplied by L to the 3/2, L and L to the 1/3. Right, so that's 1, 2, 3, or 3 to 1 KPG scaling powers, but that they are depending on L. And then we'll look at one period, gamma between -1/2 to 1/2. Right, so that's we make the period, adjust the period to be 1. And then the theorem is that under that scaling, as L tends to infinity, which is same as L and T tends to infinity simultaneously with some critical way, then we'll arrive at some limiting distribution. One can show that this is distribution. So there's a capital F of X depending on time, scale, time, and location. Okay, so we'll focus on the formula of this one. We'll describe it and then discuss, compare that with the FGUE. Okay, so this is a statement that was obtained maybe a couple or maybe 3 years ago. That result can be extended. So before I discuss the formulas, so that result can be extended to, first of all, not only one point distribution, but multi-point distribution. But here on the multi-point, it can be multi-time as well. So both time, multi-time, and multi-location distributions. And also, previous one assumed the step initial condition, but one can assume more general initial conditions, assuming that it satisfies certain very analytic technical conditions. There are some exceptional parameters that we do not have the limit theorem, but that set is really small. The exceptional points are that time is equal, location different, but the height happens to be exactly the same. Okay, so that's the only exceptional case that we do not have a limit theorem. So I mentioned this is initial conditions to be general, but satisfy technical conditions. It's not easy to, it's very difficult to check. Well, I'm not sure if they're very difficult. It's not easy to check the technical conditions on the initial conditions. The only verified cases so far are step flat and step flat initial conditions. And there are separate random initial conditions, but that's a separate computation. Because it's coming from the periodic TASEP, it should be the universal limit of periodic models in the KPG universality class in the relaxation time limit. So KPG fixed point on a ring should have the same one-point distribution as that was described above. Okay. So here the important parameter here is a tau, the time rescaled time parameter. So as I mentioned before, when time is not too large compared to L, so that means that when tau is quite small, when tau tends to 0, this capital F should be very close to the threshold of distribution, infinite TASEP case. On the other hand, when tau becomes infinity, this one-point distribution should describe more of equilibrium dynamics. So it should be expected to be close to the Gaussian distribution. So this one is should interpolate the KPG picture and the equilibrium picture as tau runs from 0 to infinity. Right. So in the next few slides, I'm going to describe the formula of the limiting one-point distribution, which I denote by capital F, and for the step initial condition, and compare that with the infinite KPG fixed point. Okay. And this is the part that is in preparation with Zipian Liu and Yomi Silva. Let's see. All right. So for the so before that, let me just recall the infinite line case. We're all familiar with this one, but I want to go through it so that we can make a comparison. For the one-point distribution for the step or narrow wedge initial condition in the infinite line case is given by FGUE, but that is FG of X if you scale the position and time and position and height adjusted correctly. So that means that the formula is that F sub KPG at time tau, location gamma, and height X is given by F sub GUE of that particular combination that's in here. The combination has this property that this distribution is invariant under the KPG rescaling. So if you take a tau and gamma and X and multiply by alpha cube, alpha squared and alpha, right, 3:1 ratio again, and that should be invariant. The distribution should be invariant. The one-point distribution should be invariant, and that you can clearly see from this particular combination of X, tau, and gamma. Yeah, right. So, and then I'll also record the Friedman determinant formula of the distribution and the Airy operator. So F sub GUE is given by the Airy Friedman determinant of an Airy operator. I'm going to take the following form. There are several different ways you can write it, the Airy operator. But I'm going to make this X not in the part of the space. So I'm going to make the space to be 0 to infinity, but put the x in this variable here. Right? And then let's recall the area function formula. The area function has the Cauchy cubic term and then Cauchy power, and then W comes up here. So this is the formula of f sub GUE. So I want to write down the actual f sub KPG in the full form. So that means that I have to change my parameter x to this combination, x over tau to the 1/3 plus gamma squared over 4 times tau to the 4/3, right? We want to put that in. So that means that I have to put that in here in x. So then probably it's a good idea to change my W, rescale in a similar way. And then maybe even scale U and V, which is in space, again in a similar way, right? So if you do that, the formula looks like this. All right. So by the way, this is the contour for this area function that you can choose anywhere between angle 90 to 150 degrees, right? So that change will happen in this way. So here's area function. Instead of W, we scale in this particular fashion, which is similar to the one that appears in KPG formula. And here's tau to the 1/3 coming up here. That comes from Jacobian factor, changing W as a variable, but W to tau to the 1/3 that comes up here. And here's some extra term that I just put in to make the final formula much nicer. So with that formula, see, I'm going to denote A sub gamma W or A sub gamma and tau of W. I have this cubic function structure. So E to the cubic function, here's tau and gamma and W appear here. Okay. So you can rewrite the FKPG at time tau and location gamma and height x to be determinant of 1 minus KKPG, where K is the rescaled area operator. So that means that it's the same, have the same structure for integral of W 0 to infinity of this new function A gamma. And here's X here and X there. Then there's a small change that I have to make. So there's a 1 gamma here. That's the parameter there. If you go through this computation, because of this factor that appear here in the gamma, I want to have to cancel it out by the conjugation that has the effect of changing to minus gamma. Okay. So the one way you can think about is that having this gamma squared that's due to the parabola. In the area process, there's a parabolic shift that should happen. And I'm putting the contribution from plus gamma and minus gamma in a combined way. All right, so this is the formula that I want to show in this infinite line TASEP case. And I want to compare that with the periodic TASEP case. Right, so in the periodic TASEP case, well, not the TASEP, but the limit of the periodic TASEP. So it's the expected KPG fixed point on the ring. The 1-point distribution takes the following form. So there's a Freudian determinant in the same space 0 to infinity. But then there's extra factor here, e to the x, c1, tau, c2, and c3, and then integrate with respect to z variable. So there's extra z integral, and there's extra factor e to the some powers. Okay, and the integral is over any circle, any small circle, so it's any circle of radius 1 centered at the origin. And then the functions c1, c2, c3 are given in terms of polylog functions. So this is the formula that's obtained by myself and then Zipeng Liu, and also independently by ProLab a few months earlier. So those are the differences. And then I'm going to focus on the formula of this Freudian determinant to compare with the infinite line case. So here's extra z integral. I don't have any good explanation why that should happen, except that the way that this was obtained was by solving the periodic TASEP transition probability by using coordinate Bethe-Andreas method. And in solving that, gradient ansatz, the transition probability will acquire this extra integral to make the formula work. But you will see in a few slides that what's the effect of this extra integral. One thing that I want to emphasize that that this distribution, unlike the KPG fixed point, is not going to be invariant under the KPG rescaling. Right? Because this is supposed to be interpolating KPG dynamics and equilibrium dynamics, so you cannot specify the KPG scaling. Another property is that this distribution F should be periodic, because it came from periodic model. So if you shift gamma by 1, this formula should be unchanged. So this will be an important point. So you can see that this exponential part do not contain gamma. So we have to make sure that this determinant is invariant under this gamma by 1 shift. All right. So I'm going to describe the determinant, Fred determinant. So I want to, so to do that, I have to introduce one discrete set. So that is that for z less than 1, or bigger than 0 and less than 1, radius-wise, consider the following discrete set. So this is S sub z. It's a solution of the following equation. So z is the given parameter, complex parameter, and solve the equation e to the minus s squared over 2 equals z. So you can write down the solution explicitly if you like. So there's a plus minus square root of minus 2 log z minus 4 pi I k, where k runs over all integer values. So pictures here. So these black dots are the Bede roots. Oh, sorry, this that discrete set, and these discrete points are called Bede roots because they came from the solving coordinate Bede ansatz problem. And they lie on a hyperbola, which extends to infinity with angle 45 degrees. And then we are going to, there are parts that's on the left half plane and right half plane. We call it z sub minus sz minus sz plus. Okay, so we're going to use sz minus in the next slide. So here's a formula for the Fred determinant. So this is the comparison. So for the infinite line case, we have the area function, or rather shifted area function. So just like the problem of periodic domains in Fourier analysis, it becomes, instead of Fourier analysis, you have to do a Fourier series. So it becomes integral becomes a sum. A similar thing is happening here. So in this periodic case, we take the sum of all s in that minus part of the Bede roots. And then you take the same exponential function, which is just exactly the same thing as in the area function, or shifted area function for the infinite line. And then we add another factor, which is s, or q function, and then divide by minus 1 over minus s. So dividing by 1 over minus s is not surprising, because so this is almost like a discretization of the area integral representation. Here, the 1 over minus s represents the spacings between the nodes, because spacings between the nodes are not uniform. So therefore, we have to multiply appropriate factor to make a discretization correct. So this 1 over s comes from that. But what makes this is not exactly a discretization, but almost, is that there is extra function f, q here. So q is some kind of function that is given in terms of polylog function, which is written in this footnote here. Okay, so apart from that, it is a quite discretization, almost same as discretization of the shifted area function. And then Fred determinant takes the formula, exactly the same formula as before, as area operator. Okay. So how does this Bede roots have an effect? So that's the part that comes in the next part here. So we have to have that this operator, this Fred determinant, or rather the operator, should be invariant if we should be periodic in gamma. So if you change gamma to gamma plus 1, this Fresnel determinant in the entire distribution should be unchanged. So if you make the gamma here to be gamma plus 1, then we'll have the extra factor of e to the half of s squared. So e to the s squared of 2, but e to the s squared of 2, that should be a solution to the Bethe equation. So Bethe equation is given by here because s is on the Bethe roots. So that makes that this function b, when gamma is shifted by 1, will have the simple transformation by a multiplication by z to the minus 1. Or for the b of minus gamma, either have this effect of multiplication by z. If they combine them together, that is invariant. So the point is that starting from the airy corner, which is the integral, if that airy corner should be changed to something such a way that it is now periodic in gamma, then if it lives in the continuous space, continuous integral here, then it's not going to happen. So it should make sense to have some kind of discrete sum there. And then this Bethe equation has the effect of exactly making that possible. Okay. And then this is true for any z. So we don't know what kind of z you should take. So we're taking some kind of average over all possible z's, and that's the outside z integral. So to summarize here, so comparison of the formulas. So for the both infinite line and periodic case, the one-point distribution functions are given by, in one case, Fresnel determinant, and the other case is determinant with the extra factor and the integral. The corners have the exactly same structure with a function f sub gamma and f sub minus gamma. We have sub gamma and in these two different formulas, depending on whether you are in the infinite line or periodic case. Infinite line is an integral, and periodic case is a discrete sum. With the exception that is an extra function that depends on the polylogal function, which I do not have any simple explanation. Right. So that's a setup. So that reminds us that in the infinite line problems and the periodic problems, in the linear problems, the Fourier transform becomes Fourier series, and then the integral changes to sum, and the Bethe roots are playing the role of this Fourier series coefficients. Right. Right, so that's the comparison of the formulas. Okay, and the next 3 slides, which will be quick, I'll discuss some 3 basic properties, which should be very natural for the periodic case. So I'm going to talk about the 3 things, which is, one is that if you take tau to infinity, and the other one is that we take tau to 0. And the third one is that the right tail estimate for all tau. So when tau is large, then we expect that it should be close to equilibrium dynamics. So when x is, so for any x value and for any gamma in this domain, in this period, one period, if you take a tau to infinity after some scale, it converges to Gaussian distribution. Right, that seems reasonable. Here's some simulations, some numerical computations of the plot of the f, and you can see that it gets close to the normal distribution. Though this is very intuitively should be true, but the proof is surprisingly technical. One has to use the, so because due to the nature of the polylogal functions that are appearing there, the asymptotic analysis involves extending the contours to a Riemann surface, and then the critical point for the split descent method doesn't appear in this natural domain, but rather you have to go to the next sheet of the Riemann surface and then comes from the branch point. So it's a little bit technical, but the result should be intuitively reasonable. The other case is that when you take a tau to be small on the other end, then the entire thing should be very close to the infinite line KPG fixed point. So if you take a proper scaling of the variable, and then when gamma is not at the not plus minus 1/2, then you go to FGUE. Okay, so that's what you expect. But when gamma equals plus minus half, then it should go to FGUE squared. So FGUE squared comes from the fact that you are at this shock location. So if there's a shock location and the Ferrari and then Leja show that it should come from the finding between two FGUE, independent FGUE. So therefore it's a max of two FGUE. So therefore we have FGUE squared. But however, this proof is not obtained completely. So at the moment, we only have the results when gamma equals 0. Other cases become surprisingly technical, so we don't have that moment yet. But however, if you look at the right tail, then now we see that this is quite reasonable. Because if you look at the right tail for every gamma, so not only just small gamma, but all gamma, sorry, all tau, so all time, not only small time, but all time. The right tail is close to the right tail of GUE when gamma is between minus half and half. And at the end points of the period, gamma equals plus minus half, that is close to the FGUE squared with some extra factors, and x tends plus infinity. Okay, so that's this is pretty reasonable because all the formulas come from sort of discretization of area operator. So in some kind of limit, that discretization should converge it to the continuous integral, and then therefore the FGUE should appear in that kind of way. The technical issues that were here and there are polylog functions appearing, which has certain non-analyticity, some branch points, branch cut, and therefore one has to handle that. That makes the computation a little bit involved, but other than that, intuitively, that's how it works. All right. All right. Right, for the remaining maybe 15 minutes, I think that's what the amount of time that I have. So I'm going to now describe some integrable differential equations associated to the Friedmann determinant. So this computation will apply for both periodic and infinite line cases. There are some small results for general initial conditions, but most of them are going to be about step initial conditions. I thought that so even though people here, many of them are, many of you are doing integrable probability, but maybe not everybody is an expert in integrable PDEs. So I thought that maybe it's a good idea to include maybe 2 slides on introduction to integrable PDEs. And then after that, I'm going to state the results containing MKDB and nonlinear equations as well as KP equations. And then I end up with the description for multi-time distributions. Right, so maybe next 2 slides about integrable PDEs. Right, so I'm going to contrast 2 things. Here's a linear PDEs and integrable nonlinear PDEs. So we want to solve initial value problems. Initial value problem, no S there. I want to examine two equations as an example. So one is V sub t plus V sub x equals 0. And the other one is here. It's the same thing, but then there's a V squared times Vx, which is like a cubic nonlinearity. Right? So this is a nonlinear version of this one, or this one is a linearization of that. So let's examine the way that people may solve the initial value problem for this linear equation. Because it's linear, and there's just t and x, 2 variables, t is time and x is space. So maybe it's a good idea to take the Fourier transform of this one, because if you think this is on the line. So if you take a Fourier transform in the x variable, then you have v hat of c t, where x changes to c. And then the x derivatives will change it to multiplication by c. Sorry, this is not k there. It should have been c. So this I c cube, because a triple derivative becomes c cube, and then v hat of t. The effect of this one is turning this PD to OD. And this is a ODE of first derivative, so you can solve it. If you solve it, then you have e to the minus I cos c cubed t. And when time equals 0, then you should put that there. Right, so this is the way you can solve it, and then you take inverse Fourier transform of this one to get the solution of v of xt. In terms of diagram, you can think as follows. So here's the initial value, v of x0. You take a Fourier transform and get f v hat cos at 0 times 0. And then you change that to the following simple thing, which is this formula, which comes in here. Right, so this time 0 to time t in the Fourier space, that change is very simple, just simple by e to the multiplication of e to its own factor. Very explicit. And then from there, you take inverse transform, and completing the diagram will allow you to make this finding the solution. Now for the integrable nonlinear PDEs, to solve the initial value problem for something like this here, what it turned out is that there is a similar scheme. So you start from v of x0 times 0, and the Fourier transform is, you cannot apply Fourier transform anymore, because if you take a Fourier transform of this one, it becomes quite messy because the multiplication of functions are not well respected under Fourier transformation. But however, there is a different transform, which are called scattering transforms. If you do that, instead of v hat, you get some other function coming up, which is called r of cos 0. And together with some other things, there are maybe 3 sets of functions that come up here. What it turned out, which is this is non-trivial thing, is that just like in Fourier space, the f hat evolves in a simple way. The evolution of this r function, or reflection coefficient, what they say, becomes quite simple. Actually, in this case, it's exactly the same kind of a pattern there. And then if you have, I didn't say what scattering transform is, but whatever that is, if there is a way of inverting it, then you can find your solution. Okay. So in this heart here is that, well, is there a scattering inverse scattering transformation such a way that you can make the evolution becomes much simpler in this transformed space, so nonlinear Fourier space. So of course, this scheme does not work all PDEs. It works only on really special PDEs. And then those PDEs are called integrable PDEs. So their scattering transformation amounts to solving some kind of, there's an auxiliary linear ODE appearing there, and you have to solve it, and x tends to plus infinity and minus infinity. So it involves solving some other problem. But more important thing here is that the scattering transformation is equation specific. So for all linear PDEs with constant coefficient of the type that I mentioned before, you can use the one transform, which is a Fourier transform. It works well for all kinds of equations. But scattering transform is not like that. Scattering transform is, if you give me an equation, maybe there is a scattering transformation, specific scattering transformation for that particular equation. And then maybe you can complete the scheme. And then the scattering transformation depends on your equation as well, right? So it's equation-specific transformation. And furthermore, the inverse scattering transformation is not a trivial thing to do. I mean, inverse transformation is also not trivial sometimes, but inverse scattering transformation even more so. Sometimes it involves a way of doing that. There are several different things, but one way is doing the so-called Riemann-Hilbert problems, okay, which I'm not going to say much, but it's a certain complex analysis problem one has to solve. But so this is a very general picture. The inverse Fourier transformation gives an integral representation of the solution of the linear PDE. Then one can do the asymptotic analysis of it using methods to be decent. Fortunately, the Riemann-Hilbert problem, which gives you, not always, but sometimes gives you inverse scattering transformation, there is a way of doing asymptotic analysis developed by Dave Zhou in the mid-1990s. So there is a parallel of this asymptotic analysis at least. All right, so let me just leave that there. there are a lot more different descriptions and properties, but let me just leave that there. And then I'll go back to our case. Right, so the theorem that I want to mention here is that for the step integral condition, if you go back to our case for both periodic and infinite line cases, if you take the freedom determinant and take a log and take a second derivative with respect to the x, which is height variable, then it can be factors as a p and r, two functions p and r. And p and r are functions of time tau and location gamma and height x, right? So function 3 variables. If you look at the function of 2 variables tau and x, that they satisfy the so-called the coupled modified KdV equations, which is mean here. So modified KdV, and KdV is one of the standard integrable PDEs, and this is coupled system, not one. There's a coupling there. In terms of gamma and x, so gamma is the location and x is height, they satisfy a different system of coupled equations, which is nonlinear heat equations. So if you drop the quadratic terms, so cubic terms, there's a heat equation, and there's extra term there. And if you take a gamma to be a complex number, then this looks like something like nonlinear Schrödinger equations. So as a corollary, it is simple to check if you have a coupled MKdV and coupled nonlinear heat equations. If you P and Q satisfy both of them, in this case here, if you take a product U to be P times R, and then it satisfies the KP equation. So KP equation is the one that appeared in Jeremy's talk a few weeks ago. So it will satisfy the KP equation that can be shown that follows from the coupled MKdV and nonlinear equations. So as a consequence, if you look at the periodic case, assuming all solutions exist, which you do not know at the moment, but the formula of F, the one-point distribution was given by integral with respect to z of e to these vectors, polylog vectors, times the Freedom determinant. And the Freedom determinant whose log and second derivative is u, so if you do the antiderivative, so this Freedom determinant is now e to the integral of y minus x of u, which is a solution of a P equation, and then y dy. So everything will depend, the solution will depend on z. So then the z is not a part of differential equations. So z should play the role of initial or boundary condition, which we, at the moment, we do not specify. So the formula here is that has the following meaning. So look at the collection of solution of the KP equation parameterized by z. So many different initial conditions. You look at the solutions, and then you build this function f for z, which is sometimes called the tau function of the KP equation. So you look at this function and then take the linear combination, average it over or many different values of initial values. Okay, so this is a superposition of the complex functions of solutions of a KP equation. This Freedom determinant or this u is actually going to be complex valued. So it's complex valued solution of KP equation. And also the fact that we had to replace the contour or the area function to the discrete sum. The discrete sum, appearance of discrete sum tells us that this is a soliton solution, which is different from the infinite line case, which is a non-soliton solution because it's related to the smooth contour. Okay, so all right. So let me make a few comments here. So this result is for step integral conditions. But however, if you just focus on KP equation, that there is a much easier way of proving it. There is a general result by Pope going back to 1989, or maybe discussed earlier or rediscovered many times. There is a criteria. If you have a freedom determinant, if the kernel satisfies certain conditions, then the freedom determinant should satisfy KP equation. So that can be checked quite easily. For the infinite line KPG fixed point for not only step but general initial conditions, Jeremy Quastel and Ramani obtained the KP equation more or less redoing the Pope's computation in a similar way. But of course, the more important result is that it's not only for the one-point distribution, but for multi-point distribution. But if you focus on the one-point distribution, that is follows from the theorem of Pope. And that method still applies to periodic case as well, not only for the step but general initial conditions. Of course, for general initial conditions, specifying these technical conditions because we do not know what kind of initial conditions really have kind of limit at the moment. But this basically boils out to seeing the following, and also that was also used by Pierre Ladouceur for KPG equation as well, and also other things. So in both cases, they involve the kernel involved the following functions: f gamma. One is shifted area and shifted discretization of it. And there's, even though there is a Q appearing there, it does not depend on any of the parameters. This f gamma satisfies this simple linear differential equations. If you take a derivative with tau and gamma, they are related to the derivatives with respect to W. So if you switch any things around, but as long as it has this structure there, gamma and this cubic factor, and that is that's what's responsible for the Pope's conditions to satisfy. Right. So this is for general initial condition for the KP. For the step initial conditions, there is some kind of extra layer of integrability. So that's what we used in our setup. So the extra layer of integrability is the following. So one can check that the freedom determinant can be switched to a different freedom determinant by taking, the usual thing of conjugating and then switching AB to BA and then those things. Where the space was from 0 to infinity, but now switched to the beta roots, not only the minus part, but the whole thing. For the infinite line case, we can do the same thing with these contours. And then this function H has the following structure. The kernel has the following structure, which is that the apart from 1 over U minus V vector, the top part is a sum of terms which can be factorized in terms of U and V. So it's like a tensor product, finite rank operator divided by U minus V. And yeah, so in general, those operators called integrable operators. So integrable operators are operators of the form this type of sum divided by U minus V, and they were singled about 30 years ago. Many interesting operators in the random metric theory are integrable, area operator, sign operator, or the Christopher W kernels on the unitary ambient ensembles. And it's also known that the operator that appears in the Airy process, which has lots of derivatives and complicated formulas, that can also be transformed to integrable operator. That also work by Bartolo and Capasso. The integral operators have this property that its resultant is also integrable operator. And another thing is that the resultant can be obtained by solving a Riemann problem. So in our specific case, because of the structure of the formula, the special structure associated to the integral operator is translated to the special structure of the Riemann problem. But the introduction to integrable PDEs, I mentioned that the Riemann problems also arise in solving integrable PDEs. So one can compare to see if this remarkable problem that arose from this integrable operator can be recognized as one of the ones that appear from integrable PDEs. And the structure that arises is involving this cubic function. And this is the one that is studied extensively. It's one of the most fundamental remarkable problems that people have studied. And especially if this is just a quadratic function that is a nonlinear Schrodinger equation, if it's a cubic function with a quadratic term missing, that is the modified KP equation. So from that, one can recognize that this problem is related to NKTB and nonlinear Schrodinger equations. And therefore, you can compare those formulas and you can conclude that the function P and R that I mentioned are going to solve these integrable PDEs. Right, let me just make one more slide. Sorry, I'm going over time here. So just one slide here. So it's for the multi-time distribution for the step initial condition. There is a similar results obtained for not only multi-location, but also multi-time. There's a similar formulas obtained for the periodic case, and also infinite line case, there is also similar formula by Zipeng, Liu. And then there's a kernel there, the prime determinant. One can check that this operator can be written as an integral operator, as like the one-point case. And some computation that I'm doing with Prokhorov and Silva shows that that multi-point distribution can be related to the matrix NKDB and matrix nonlinear heat equations and the matrix KP equation. The matrix KP equation is the one that's obtained by Quasar-Riemann for the infinite line TASEP, infinite line KPZ fixed point with general initial condition, but for the equal time, and this one extends to multi-time, but only for the step initial condition at the moment. Right, okay, so let me just stop now. Right, so thank you for your attention.
All right, thank you very much, Jinho. So we definitely have time for questions for Jinho. So just unmute yourself and ask. I'll start with a question though. So one of the values of having these connection to integral PDEs is to extract tail behaviors very precisely,
yeah,
and stuff like that. And I know that Pierre Ledoux-Salle, I think, wrote a little bit about this for KPZ in relation to the KPZ equation in relation to KP equation. Have you thought about what this tells you about tails of the periodic model?
Yeah, so so here are the further questions that needs to be addressed but not done yet. So here's that's exactly the same sentence. Mm-hmm. So one may ask, what's the good use of having integral PDEs, right? So as you said, the more important, at least from my point of view, is that it is related to Riemann-Eibel problems. The Riemann-Eibel problems gives a tool of getting detailed asymptotic formulas. So that's something that's not been done. So yeah, that's in my to-do list, but it's not done yet. So hopefully that will give us some detailed asymptotic analysis for the periodic case or multi-time distribution in the infinite line case for different type of asymptotics. So that's not done yet. Yeah.
Thank you. Other questions? Tamara, I see you unmuted.
I have a question. Hi, Jinho.
Hi.
So I didn't, thank you very much for the very nice talk. I didn't understand very well. So which kind of initial data you associated to? So it's not periodic. So for KP, it's periodic in gamma only, no? That's, so the initial data of the PDE that you are.
Oh, yes. Yeah. Okay, so that's another point here. The initial and boundary condition for the integral PDEs are not yet determined. So that's not.
Okay, yeah. So it's point 1.
Yeah, so at the moment we do not know. So yeah, that's something that we have to take t to 0 and then have to see what kind of behavior that has. Mm-hmm. We don't know that yet.
Mm-hmm.
Yeah, so you only know that it's periodic in gamma. So when you have
Right.
KP, you have periodic in gamma, and the rest is unknown.
Right, that's right. Yeah, yeah, that's something that has to be studied. Yeah.
But I was looking, sorry, at the paper of Prolak that he was mentioning KDV instead in his paper with this
So
periodic.
Pop has two papers. I mean, several papers, but he has a similar result for KP and KDV. So KDV paper is earlier. So that is another similar setup. So there's a fragment determinant of some operator. The operator depends on two parameters, X and T. Under some conditions on the kernel, he sets the fragment determinant results by KDV equation. And then a few years later, he extended that to 3-parameter case and then the KP equation.
Yes, but so it was while you get modified KDV in your case.
Oh, so for the modified KDV, right. So the modified KDV appears here because sorry, so modified KDV appears because so here P and R, if they satisfy some symmetric condition, right? So P is equal to R. Yeah, if P equals is R or P equals minus R. Oh, sorry, MKDV versus KDV. Okay. Okay, so
but there is Mura transform. Okay, yes.
Yeah, that's right. So so you can think of the following way. So if you have a Tracy-Adams distribution for GUE, even though Penn-Levé solution appears, what actually appear in this formula is that you have to take a Q squared, right? So in other words, you have to take integral of Q squared is the one that appear in the GUE formula. So that transformation is similar to the Miura transformation.
I see.
And then that's the one that corresponds to the step or GUE related cases. If you have a flat case, F1, then you have both that integral of Q and also integral of Q squared and then Q both appear. And then therefore, that's the case, then you'll have a KDV. So if you do the same thing with the flat initial condition, which I didn't mention, if you have the flat initial condition, then the KDV will appear. And then they are related by, the MKDV and KDV are related by the Miura transformation.
Okay, thank you.
Jinho, sorry, but perhaps I should add. So what Tamara was mentioning, so that Prolak mentioned in his paper is exactly about the flat initial condition. I guess he hints at he hints at the KP for the periodic TASEP with step initial condition. He hints at it. So basically we covered that hint that he gave. But for the flat, he has even some multi-line argument to get the KDV, not modified, but the KTV. And we recovered that as well for the flat initial condition. So playing around before the periodic TASEP with flat initial condition, we indeed get the KDV. That's also what Prolak mentioned.
Oh, yeah. Okay.
Questions, comments? Yipeng, did you have? No? Okay. Okay, so let me just I reminded people earlier this morning who were on, but I'll do it again. Next week, so there won't be a Friday lecture, but there will in its place be lectures every day as part of the mini course section of this ongoing summer school. And I just sent the link to the website in the group chat, and I'll give people a little while to click on that. And to the first lectures will start on Monday. And if you click on the mini course program, you'll see a variety of lectures. The lecturers are Hugo Dumigno-Copin, Fabio Toninelli, Michael Wheeler, Greta Penova, and Richard Kenyon. And they'll be giving 3 lectures each over the course of this coming week. So I hope to see many of you there. And we'll resume not this coming Friday, but the following Friday with our research component, and we'll have a few more Fridays, maybe 4 or 5 more Fridays of lectures. Okay, so let's all thank Jinho again for a very, very nice talk.
Thank you very much.
Hope everyone has a nice weekend, nice evening if you're in Europe, nice morning if you're in the West Coast. Okay, bye.